Okay, good morning, students. Welcome to the today's class. I think better. Just a second. So in the last class, we have seen the layout diagrams. This is what I have posted in the Moodle's video link as well. So I thought that you have seen once. So let us continue with another layout diagram. CMOS NAND gate. We shall draw the CMOS NAND gate, and then we'll move on to the next concept. Okay. So according to my plan, today's topic is basic circuit elements. According to the lecture plan, I would like to discuss about the lecture number 5, basic circuit concepts. Basic circuit concepts. Okay, before going to that one, what is exactly the basic circuit concepts and all? I would like to discuss about, let us recapitulate what we have seen in the last class. Recap, let us do. So we have drawn the layout diagram for a particular CMOS NOT gate. I would like to discuss about the CMOS NAND gate layout diagram. Okay, CMOS NAND gate layout diagram. Okay, so it will be recapitulation what we have seen yesterday. Layout diagram. Okay, so what is the prerequisite for drawing the layout? Circuit diagram is important for us. Okay, let us draw the circuit diagram. So CMOS NAND gate, how do we draw? The symbolic representation is this one, NAND gate, right? Logic diagram. So logic diagram. What is the logic diagram here? Logic diagram is this one, NAND gate. What is the logic expression? A, B, and Y. Logic expression is A and B whole bar. So this is what the logical diagram. Then what is the circuit diagram for this? Circuit diagram. So since two variables, two inputs we have taken, therefore two transistors that we have to consider at the pull down network, right? So two transistors we have to consider. Why we need to take the two transistors, all this information we have already seen. And the parallel connection that we have to take, similar number of transistors, but PMOS the two opposite connection. If it is in bottom transistors are in series, upper transistors are in parallel. So that's how we have to do it. Therefore, this is called VDD. This is called the ground. This is called A, B. Let me call A and B. This is called Y. So now, what is the stick diagram for this? So what is the stick diagram for this? I think today's net is very slow. Now we should draw the stick diagram. Okay, stick diagram. What is the stick diagram for this? I have to take two metal lines, top one metal line, bottom another metal line. Stick diagram means these lines are very straight lines that we have to draw. Okay, don't write just like that. Okay, and two PMOS transistors are required according to this notation I'm doing. Okay, this is the one yellow diffusion. This is another yellow diffusion. Okay, so another diffusion, N diffusion for NMOS transistors. This is the one transistor. This is one transistor, another transistor. Fine. So these two are connected here, and take and extend this to this point. Okay, something like this. Now, how do we provide a connectivity between these two, this upper transistor and lower thing? So with the help of metal line. So I'm going to use a metal here. So since the metal I'm using, so here the contact cut is required, another contact cut is required, another contact cut is required, another contact is required here as well. So in the circuit diagram, it is not necessary to connect A to A, B to B, something like this. So it is not necessary to connect A to A, B to B, something like this. But in a stick diagram, we have to connect it properly. So we are going to use the stick diagram. I'm extending this polysilicon from here to here, something like this. Okay, so just you have to draw the straight lines. So okay, don't write like that. Something like this. It will like a triangle. So it's not good. It's not correct as well. So we have to take the straight line and draw, connect it here, because stick cannot be bent. Okay, so that's it. So the B is connected in this way. So B is I'm going to connect in this point fashion. So why can't you connect the B at this time? So in this because if I do like this, there is a short circuit is here observed. So without any contact cut, if the same materials are crossing each other, then connection will be established. Therefore, we don't want to use this kind of approach. Okay, so that's the thing. So here it does not have any problem. I'm extending the output signal something like this. This will be my output. Okay, so this is my input. This is my input. This is called A. This is called B. This is called Y. This is called Y. That's it. And I am going to introduce the substrate connection as well. Okay, this kind of information that I have in previous lectures. How do we have? How can we draw all these things? Okay. Now I'm going to draw the layout diagram for this one. Layout diagram. So how, in which way that we have drawn the stick diagram, the same way that we have to draw, but we have to apply the design rules. Okay, so the design rules concept also we have seen in the last third lecture. So please go through it once. Okay, so I'm going to draw here the stick diagram layout diagram. For that, I'm going to consider I want to consider the 4 lambda by 4 lambda thickness VDD I have used it here. Okay. So another line that also I have to use for the sake of showing all these things, I'm using this one. Okay, so what is the minimum width of this? What is the minimum width of this metal line? This is for VDD. The minimum width is 3 lambda we have to maintain here. So minimum 3 lambda, but I want to consider the 4 lambda. Okay, why? Because the contacts I want to consider for the contacts overlap region is 4 lambda by 4 lambda. Therefore, that's the reason why I'm interested to use the metal width is 4 lambda. 3 lambda is sufficient. There is no doubt at all. But for the sake of contacts, this type of contacts I'm using, right? So these contacts is overlap region is 4 lambda by 4 lambda. That's the reason why I want to extend the metal to 4 lambda, not 3 lambda. Okay. But if you're not interested to use the 4 lambda, use the 3 lambda only. Okay. Now the diffusion lines are required according to the notations there. Okay. So yellow diffusions are required. So here, how can I do this one? Okay. This is the one diffusion. Okay, it's a 2 lambda by 2 lambda is the thickness. I need a square box, right? Okay, for the square box means again I have to do this. Okay, this is also connected at this point closely. Okay, next I need to draw another line. Copy, and I want to paste it here as well. Okay, and again I have to draw another line here. I hope that's fine. Okay. I think this should be somewhat lengthy. Okay, fine. So therefore, this diffusion line is 2 lambda by 2 lambda diffusion line. Please remember. Okay. So let me draw these lines. This is the hash lines for the metal. These are the metal lines. Okay, so this is the diffusion line. Forward slashes, but a spaced slashes that I want to use. This is the just simple representation, nothing more than that. If you fill the colors, it's okay, because sometimes we are not able to fill with the colors. Okay, and it is better to take another thing also here. Okay, sorry. Okay, fine. Now what I have to do, I think better I have to move this somewhat lower distance. Just whenever you're trying to draw these layouts, you should have some kind of estimation. Okay, so because we have to follow the design rules, right? Now I'm going to use diffusion line. Another shape also I am going to consider. Okay, I'm sorry. This is the diffusion line. So therefore now polysilicons are required. One polysilicon is required here. 2 lambda by 2 lambda polysilicon. Here also we should take copy and paste it here. It takes some time, okay, but damn sure one question will come in your main examination. Similarly, I have to consider another.
So in today's exam, do we have any questions on this topic?
Yes, obviously.
Should we need to draw these diagrams, sir?
Yes. So these are the things. So what we do is that yesterday also I posted that lecture, no. If you have the color codes, fine. If you don't have any color codes, use the black color, but this type of hatches that you have to show. Okay, so that's what you have to remember. Okay, this is what we can draw it here. Just what happened here is that I can draw freehand with the free hands, but sometimes it's not look good. Something like this. I can also draw here with the free hands. Okay, so at the middle, we need to have one metal there. So its size is 3 lambda, minimum 3 lambda we have to maintain. So that's it. Okay. Fine. These lines should be there here. So contact cuts that we have to provide. Okay. So one contact cut is 4 lambda by 4 lambda contact cut is required. So metal related contact I'm interested to write. Metal contacts. Since that is a 4 lambda I have taken, therefore overlap region also 4 lambda I have considered. Okay, so metal line I need to draw. So it's consisting of 2 colors. So one is blue lines and another is these lines. In between, we need to have a contact cut there. Okay, so I have to consider this one. Okay, copy, and I want to paste it here somewhere. Paste. So I have to consider this one at this point as well. So what is this overlap region? This is blue color. Also there is yellow color. Okay. Whereas at the bottom, we have to consider green related, green overlap region, green and blue. Okay. And I'm going to consider another shape. So therefore it is the combination of two colors, blue as well as green. So there is a contact cut at the bottom. Right. So the similar contact is required. Similar contact is required. Copy. Similar contact is required here also, but it is a blue overlapped with green overlapping and consisting of these lines and the hash lines. At the bottom, the contact cut is required, right? That's it. So we can extend this metal from here to here. The metal we need to extend. We need to extend the polysilicon. We need to extend the polysilicon here also. So this is called A, this is called B, sorry. This is called B. This is called Y, okay? That's it. We have drawn the layout for this one. So what is what is the final thing that we have to see here? The P well is required. Therefore, I'm going to draw, sorry. I'm going to draw one shape here for the P well. So this is the reason for the P well, okay? So we have to maintain some distance here. Of course, the substrates also required, okay? For the PMOS transistor, N substrate is required. Therefore, N overlap region is we have to consider. Similarly, I have to consider the metal lines also. And we have to use the metal contacts. The contact cut is required there. Okay. Similarly, we need to provide the P substrate for the NMOS transistors. And I'm going to consider these things. So for the sake to reduce the time, I don't want to use the hash lines more and more. So please remember that it's a 4 lambda by 4 lambda. Okay, so contacts are also clear. Now another thing is that P plus masks are required. So yellow color P plus masks are required. For this yellow color P plus mask, only we have to use wherever P regions are there. For those P regions only we have to draw. Similarly, these are the P regions are there. P plus mask is required for these PMOS transistors as well. Okay, just you have to show the P plus masks as well. Okay, so therefore this is called P plus mask. While we are realizing the NMOS transistor, PMOS regions must be masked. So that's what we want to say. So what is this one? This is P well. This is called P well. So therefore we have used the P well process. So only the design rules here that we have to consider is P plus mask to P well. We should maintain some distance. We discussed this point in the last class. Okay. So this is a very quick way that I have drawn the stick diagram, sorry, layout diagram for the CMOS NAND gate, which consisting of 4 transistors. But it is a practice actually. Once you twice and thrice that you draw this one, you can understand how effectively that we can draw this thing. Okay. Please remember that we have to follow the design rules. So the design rules are very important. So for example, I will say one design rule here. So what is the design rule here at this point from here to here? So we should not be very near to each other, those polysilicons. Minimum 2 lambda distance should be maintained. Okay. So that's what very important here also. So from in this one to this poly also, we have to maintain the distance properly. Okay, so alage P plus 2 P well. So we have to maintain the design rule here as well. Okay, so in this direction also we have to maintain the design rule. So like this, whatever the design rules I have discussed previously, we have to follow the design rules. What is the design rule for the contacts? What is the design rule for the width of the diffusion? What is the width of the polysilicon? What is the width of the N diffusion, P diffusion? What is the size of the contact cut? What is the size of the overlapped region? All these things you should know. Okay, once we know this one, you can easily draw the layout diagram in this way. Almost you have got 6 marks or 12 marks question you will find in your main examination. Okay, fine. By the way, these are the different ways that we can draw the layouts. So when time permits us, we will do the more layouts in the coming classes. Up to this point is more than sufficient. Okay. If you want to draw the monolithic diagram, for example, I will show you one diagram. So that way also you can do it. I will show you that diagram once. By looking at the diagram also, you can see what is the copy and then I want to paste it here. Can anybody tell me what is this diagram is? Anyone from the class? What is this circuit it is? So I have drawn the layout. Suppose, for example, if you don't have any color codes, for example, you don't have any colors. Okay, then you have to, if you want to draw the layout, so you can draw in this method also. Okay, but remember that you have to draw the hash lines properly. Okay, can you tell me what is this the output? What is the output of this circuit? So as we know that this is a VDD, right? So this is VDD, right? So it is VDD. So what is the length that they have taken here? It's a minimum 3 lambda, but they have taken 4 lambda. So 4 lambda they have taken. Here also they have taken 4 lambda metal 1. Okay. Now, so this is the depletion type mode transistor. This is a depletion mode type of transistor. Depletion mode transistor. So the diffusion is extended towards this side it is moving, and this side also it is moving. Okay, so the output is taken here. So one polysilicon is here, another polysilicon is here. So I have shown up to this point only, but what he has done, so he has extended the metal, so polysilicon towards the metal side. Doesn't matter. Okay, so unless otherwise, if you don't have any contact cut, the metal can cross the diffusion, metal can cross the polysilicon. It doesn't matter. Okay, so therefore the polysilicon can cross the metal line. We don't find any problem. So therefore, something like this, we have a depletion type mode transistor, okay, and connected here, depletion mode type of transistor, and here is one transistor is here, another transistor is here, something like this. It is there, okay. So therefore, what is this? What is the circuit diagram is? So A plus B are there. because of the depletion mode type of transistor, NOT gate is there. Therefore, it is called simply NOR gate. It is simply NOR gate. Okay. So I have defined what is this one is called. This is implant. This is implant. So what is the implant? What is what is the what we can call it as design rule for the implant? So from all the directions of the channel, this is the channel, right? So the length of this channel, this is the length of the channel. Okay. And this is the width of the channel, right? So all the directions of the channel towards this side, towards this side, towards this side, towards this side, we have to maintain minimum 2 lambda, minimum 2 lambda, minimum 2 lambda. Okay. So therefore implant is actually from the channel. For example, this is the channel. This is channel. In all the directions, we have to maintain minimum 2 lambda, 2 lambda, 2 lambda, 2 lambda, 2 lambda, right? That is implant related design rule. Now, so buried contact is required, right? Buried contact, where the buried contact is required? The buried contact is required at this point. The buried contact is required at this point. So at the bottom of the channel, towards the diffusion side, how much maintain? 2 lambda we have to maintain. So therefore, this is the diffusion side. Alage diffusion, it got diffusion on there. But here also we have to maintain minimum 2 lambda. So therefore, what is this length of this overlap region of this contact? This is a 4 lambda. Okay. And towards the polysilicon side, means this is the polysilicon side. This is the polysilicon side. I think you observe what is the point that I'm discussing about. Okay. So towards the polysilicon side, 1 lambda is we have to maintain from here to here 1 lambda. So from here to here, we need to maintain 1 lambda. So that's what we have to remember. So just more clearly, I will write it here. So here what I'm saying that at the contact I'm talking about, this is what the contact, I can say that. This is the contact to overlap region. Okay. Okay. So, so this is what actually the contact they have produced. So how they have done this one, another question. So what we have to do is that at the bottom of the channel, this is the bottom of the channel. Towards the diffusion side, 2 lambda we have to maintain. So here bottom towards the diffusion, this is also towards 2 lambda we have to maintain. But towards the polysilicon side, means this side, we have to maintain 1 lambda. Towards the polysilicon side, 1 lambda. So this is what the polysilicon, right? These are the polysilicon. These are all the diffusions. So therefore, that's the reason why this should be 4 lambda it came about. Okay, this should be, this is the 1 lambda, 2 lambda, 1 lambda. This is also 4 lambda. So therefore, so within the so the buried contact overlap region is buried contact. This is called buried contact. Buried contact. So this is a 4 lambda we have maintained. This also 4 lambda we have maintained. Right. So that is a small design rule for the depletion mode type of transistor. Since here we need to have a buried contact is required because the polysilicon and diffusion are connected together at that particular point. Therefore, we use buried contact. Its dimensions according to the design rule. Fine. Fine. So by looking at the layout diagram also, it is possible to say what kind of circuitry it is. Now let us quickly move on to another concept that is called basic circuit concepts. So far so good. What we have done, once we have a symbolic representation of the circuit that we have materialized with the help of mask layers. Okay, so what we have done, so far we have done the translation of circuit into layer form. circuit into layout. That's what we have done. So estimating the performance of the circuit, estimating the performance parameters of performance at the circuit level is not that much accurate. Okay, estimation of performance parameters. Performance parameters. What do you mean by a performance parameters? Like delay, power. Okay, these kind of things. These are called performance parameters. At circuit level is not accurate. Okay, so what we can do it? We can do the estimation, hence we can do the estimation at layout. So which gives you the more accurate values, okay, which gives more accurate values. Clear? So that's what we have to understand about it. So in order to do this one, first and foremost fundamental concept is sheet resistance. Sheet resistance. Finding the sheet resistance of a material is the one thing. The second one is area capacitance. Area capacitance. So these two things are required. Most of the cases, resistance and capacitance we normally consider to find out the delay of the circuit. Okay, so these are the two basic circuit concepts we need to consider in order to estimate the delay of the circuit effectively. Okay, so let us talk about the sheet resistance quickly. The first one is sheet resistance. What do you mean by this? So the sheet resistance is something like this. For example, you consider okay. For example, this is one material. So this is called metal. For example, it's a metal, aluminum metal, for example. If you want to find out, the resistance from A to B, what we can do? From A to B, I want to calculate the resistance of this material. Okay, I want to calculate the resistance of this material. So what I can do then? What is the fundamental? So far we are not talking about a simple wire. So this wire consisting of okay, some length, is having some length, right? Having some thickness, so sorry, having some width W, length, width, and there is also thickness is also there, right? Some thickness is also there. So from here to here, the thickness T, for example. So therefore, it's not simple like wire. It consisting of the physical material having length, width, thickness. Okay. Under the situation, if you want to find out the resistance offered by this material is, for example, RAB, resistance from A to B. How do we calculate? The fundamental equation is rho L by A, cross-sectional area, as everybody knows about it. Okay. So what do you mean by resistance what do you mean by the resistivity? R rho stands for resistivity. So resistivity is a fixed value for different materials. So metal has some resistivity Polysilicon has some resistivity. N diffusion has some resistivity. Okay, what do you mean by resistivity? It is the ability of the material to oppose the flow of current, nothing more than that. Okay, so therefore each and every material has an ability, some kind of ability is there to oppose the flow of current. Okay, so therefore that is called resistivity. As we know that length is L, L stands for length of the wire or layer. So A stands for cross-sectional area, cross-sectional area, right? It is a cross-sectional area. Therefore, how do we calculate now this one? What is the cross-sectional area in this sense here? Okay, rho L, fine. I'll consider rho L, but A is the cross-sectional area, means this one, right? So you can observe that the cross-sectional area is something like this. This is what the cross-sectional area. So what is the cross-sectional area for this one? So it is simply this is the width, the thickness will become a width of this one. The width, actual width of this one is the length of this particular area for a particular piece, right? So E piece, for example, you consider this one, the width becomes the length for that particular phase, and thickness becomes its width. Agreed? So therefore, what we can say that, so we can write it as thickness into width, that we can write the cross-sectional area. Okay. Now we write one point here, which is equal to rho by T. Rho by T is multiplied with L by W. So L by W is actually physical quantity. Okay, therefore the length and widths are the designer that is there in the designer's hand, whoever designed the material, but rho and T will be the fixed for that one. Okay, now let us, therefore this is how we have to calculate the RAB, right? So this is how we have to calculate the resistance offered by this particular material. Let us consider one case. What if L is equal to W? What it signifies? Length and widths are same. If the length and widths are same, it becomes a square material that we are talking about, right? We talk about the square material. So therefore, now RAB, whatever the RAB that we have considered, is nothing but rho by T only. Rho by T only. Now this is called the sheet resistance, RS. This is called the sheet resistance. Is it clear? This is called the sheet resistance. So how do we define the sheet resistance now? For a square area of the material, whatever the resistance that we calculate, that resistance is called the sheet resistance. Right? Whatever the whatever the material that we have considered, if you take a square area, if you want to calculate the resistance of that square, that we can call it as a sheet resistance. Right? So therefore, the sheet resistance is completely depending upon, therefore RS is a completely function of rho and thickness. It does not depending upon the length and the width of the material. Okay, what does that mean? For example, if consider this is the square, one square I am considering. So this is another square. For example, this is another square, right? As long as the thickness of T1 and T2 and T3 all are equal to particular T, thickness all are equal, but length and width of all the materials are for a particular square is same. So therefore, here RS1 is equal to RS2 is equal to RS3. So therefore, it is called RS1. This is called RS2. This is called RS3. So therefore, so the dimensions of, as long as you take a square area, the sheet resistance of all the materials are same. How big the square is, it doesn't matter. Okay, because why it is so? It is completely depending upon the resistivity of the material and thickness of the material. Please remember that the thickness of the material should be same. Right? So that's what we can understand. So therefore completely we can understand that what is the sheet resistance of different materials, whatever the materials that we are using here, polysilicon we are using, diffusion we are using. Okay, and another materials, what we have used in another thing, polysilicon we are using. Okay, these are the different materials that we are using. All right, what I can do is that what are the different sheet resistance that are available for whatever we have considered so far, layers. So these are the layers generally we are using in your layout diagram, right? So what are the different layers that we have used here? So these are the different layers, right? So therefore, you can see at different technologies. I have considered at different technologies. For example, here I consider, here I have considered 5 micron technology, orbit 2 micron technology, 1.2 micron technology. These are the different technologies that I have considered. Okay. So for each and every technology, its thickness is different. Here the thickness is somewhat, here the thickness is different, here the thickness is different. Okay. So that the thickness of these technologies will be different. Okay. So consider the metal, consider the N diffusion or a P diffusion, consider the silicide, consider the polysilicon, consider the N channel, consider the P channel. Okay. So the sheet resistance of metal at 5 micron technology is 0.03 ohm per square. So what is the what is the units for this one? Ohm per square. Ohm per square. Ohm per square. So what is the units for the sheet resistance, by the way? Ohm per square. So therefore 0.03 ohm per square for a metal at 5 micron technology, where the resistivity will be defined for the metal and thickness will be defined from the technology. Okay, so therefore 0.04 for a metal at 2 micron technology, orbit 2 micron technology. So therefore here what we can observe that the resistivity of the metal is same. Okay, irrespective of the technology that we are using, the resistivity is the same. Okay, but where the changes, why these kind of changes are there for the metals? Because of the thickness. Thickness is different for the different technologies. So therefore, even though therefore for micron technology, T1 will be there. Rho is the same for this one, but T2 is different. Rho is same for that one. T3 is different. So therefore, this is for my 5 micron technology. This is 2 micron technology. This is 1.2 micron technology. Did you understand what I'm trying to say that here? The resistivity of the metal is the same, but thickness is different for different technologies. That's the reason why we have a different sheet resistance for metal at different technologies. For it is an N diffusion. So normally it is an N diffusion. So that means source and source we are talking about. Source and drains are realized by N diffusions, right? It will be 10 to 15, 50, 20 to 45, 20 to 45 will be there. So for example, if you consider the P diffusion, just 2.5 times you have to multiply this one. 2.5 times of this one will give you the P diffusion sheet resistances. Generally, we know that. Silicides is one of the important thing. This is the mixing of polysilicon and metal in order to reduce the sheet resistance. We do this one. Okay. So this point we will talk about later on. It is 2 to 4. But whereas the polysilicon sheet resistance is 15 to 100, 15 to 30, 15 to 30 will be there. It's very important. N channel, if we try and consider N channel diffusion, it is 10 to the power of 4 ohm per square sheet resistance can be observed. Whereas at 2 micron technology, 2 into 10 to the power of 4. This is also 2 into 10 to the power of 4. How did you get this one for P channel? Just they have multiplied by 2.5. So therefore, 2.5 into 2 into 10 to the power of 4 is nothing but its sheet resistance. 2.5 into 2 into 10 to the power of 4 is its sheet resistance of this. So therefore, this is how we have to use we have to identify the sheet resistance of a material. So what I can do, why I am going to consider here is that how big the circuit it is, how big the layer it is. Just I have to convert it into different squares. I have to convert it into different squares, right? So different squares that I will consider. Okay, so therefore I can calculate the length of this one is, for example, this is the length of this one. Okay, this is the length of this one. This, for example, this is the width of this one. I can calculate it very easily. But instead of saying like that, the resistance of any layer will be the dimensions of that material is multiplied with its sheet resistance. So this is what the point of interest that we need to do. This is how we have to calculate the resistance of a material. Okay, so we do the remaining things in the next class. Up to this point, there is examination in the afternoon. You please go through it once. Okay. If you have any doubt related to the examination, so you please send me a mail, or otherwise type it in the chat box. We can clear that doubt.